at 1:00 a.m. Eastern Standard Time on December 19th, an interstellar object passed Earth at its closest point ever. Most people never noticed. There was no flash, no headline moment. But inside the data recorded during that brief passage, scientists are now finding details they did not expect to see. And to understand why that matters, we need to start with what actually happened during the flyby. The moment of closest approach is now behind us. 3. Atlas has completed its flyby and is already moving away from the inner solar system, continuing its journey back into interstellar space. It did not slow down. It did not linger. Whatever this object was willing to reveal, it revealed it during that narrow observational window. What makes this event significant is how rare it truly is. In all of modern astronomy, only 3 interstellar objects have ever been confirmed entering our solar system. Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2025. 3 visitors, separated by years, each one different from the last. At the time it passed Earth, 3I Atlas was already traveling at extreme speed, positioned at roughly 1.8 astronomical units from our planet and accelerating outward. There was no realistic risk of impact and no possibility of capture by solar gravity. From a planetary safety perspective, this flyby was calm and uneventful. From a scientific perspective, however, this moment was anything but ordinary. Objects formed around other stars preserve chemical signatures shaped by environments far beyond our own solar system. Different temperatures, different radiation fields, different elemental ratios. A close flyby like this offers a fleeting chance to observe those signatures before the object disappears forever. Scientists have emphasized that opportunities like this do not repeat. Once 3I Atlas moves beyond the reach of our instruments, the chance to study it directly is gone. What we manage to capture during this passage will shape how we understand this visitor long after it fades into the dark. But what is truly intriguing is that the latest observations today may be revealing unusual compounds and abnormal physical properties within this comet itself. So what exactly are they? Recent images captured by the Gemini Observatory show 3I Atlas, glowing with a distinct green to greenish blue hue. At first glance, it looks beautiful, almost decorative. But in astronomy, color is never just aesthetic. It is information. And in this case, that color is acting like a fingerprint pointing directly to the chemistry of the object itself. In comets, green emission is most commonly linked to the presence of diatomic carbon and cyanogen, often referred to as C2 and Cn when described in spectroscopy. These molecules do not exist freely for long. They form when carbon-rich compounds trapped in ice are broken apart by solar radiation. When sunlight hits the coma surrounding a comet, these fragments become excited and re-emit light at very specific wavelengths. Green light is one of those signatures, and seeing it tells scientists that active gas release is taking place rather than simple reflection from dust alone. This process becomes more pronounced as an object approaches the sun. Increasing heat causes volatile materials such as carbon-based ices and other frozen gases to sublimate, transitioning directly from solid to gas. As these materials escape the surface, they expand outward, forming a glowing envelope around the nucleus. In the case of 3I Atlas, the intensity and clarity of the green emission suggest that this volatile-driven activity is not weak or residual. It is ongoing, structured, and chemically rich. What makes this particularly interesting is how this behavior compares to ordinary comets formed within our own solar system. Most familiar comets are dominated by water ice. As they warm, water vapor drives their activity, and the resulting spectra follow patterns that astronomers know well. Carbon-based emissions appear, but they are often secondary. 3I Atlas does not fit cleanly into that pattern. The balance between gas and dust, and the prominence of carbon-related emission, suggests a composition that may not be water-dominated in the way typical solar system comets are. That difference matters. An object formed around another star would have condensed in a protoplanetary disk with a different temperature profile, radiation environment, and elemental mix. The ratios of carbon, nitrogen, and oxygen locked into its ices could reflect chemistry shaped far beyond our sun's influence. The green glow we are seeing may therefore be more than a surface effect. It could be a direct window into the building blocks of planets formed in another stellar system. In other words, the color of 3I Atlas is not simply telling us that gas is escaping. It may be telling us where this object came from, what kind of environment shaped it, and how different that environment might be from our own. And that raises a much larger question than color alone ever could. If color and gas emissions can hint at an origin beyond our solar system, then are there other clues hidden in the object's motion itself that tell the same story? One of the strongest pieces of evidence that 3I Atlas does not belong to our solar system comes not from its brightness or its chemistry, but from the path it follows through space. Its orbit is retrograde and tilted by nearly 175 degrees relative to the plane in which the planets move. In simple terms, it is traveling almost head-on against the general flow of the solar system. Objects born here do not behave this way. Most planets and native comets orbit the Sun in roughly the same direction and within a relatively thin disk. This shared alignment reflects how the solar system formed from a rotating cloud of gas and dust. Even comets with highly elongated orbits still tend to respect that overall structure. A retrograde orbit that's steeply inclined is therefore not just unusual, it is a clear signal that the object was not shaped by the same gravitational history. When astronomers compare 3I Atlas to the two interstellar visitors that came before it, the picture becomes even clearer. Oumuamua followed a hyperbolic path with no inclination to return, while Borisov arrived on a trajectory more similar to a traditional comet, but still unmistakably unbound to the Sun. Each interstellar object we have observed has taken a different route through our system. What they share is not a specific orbit, but the fact that none of them fit into the solar system's orderly architecture. As 3I Atlas moved inward, its trajectory was subtly influenced by the gravity of major planets along its path. Encounters with Mars, Venus, and most strongly Jupiter introduced small deflections, bending its course without capturing it. These interactions act like fingerprints, allowing scientists to refine orbital models and confirm that the object arrived from interstellar space and will leave the same way. The key point is that despite passing through a crowded gravitational environment, its speed and angle remained consistent with an object merely passing through. Not one settling in. By reconstructing this orbit backward in time, astronomers can estimate where 3.1 Atlas came from and how long it has been traveling between stars. Looking forward, the same calculations tell us that it will never return. Its path is a one-time crossing, a brief intersection between our solar system and a much larger galactic flow of material. In that sense, the orbit of 3I Atlas is not just a trajectory, it is a timeline, recording both its distant origin and its inevitable departure. And if this orbit already tells us so much about where 3I Atlas came from and where it is going, then the next question becomes unavoidable. What else can we learn by studying how it interacts with light itself? The observations of 3I Atlas did not come only from telescopes on Earth. As it passed through the inner solar system, space-based instruments were also in position to watch it, including the Europa Clipper spacecraft, which captured rare images before the object began its final departure. These observations are especially valuable because they were made above Earth's atmosphere, free from distortion, at a moment that will never repeat. Europa Clipper's ultraviolet spectrograph provided insight into the structure of the comet's head and tail in wavelengths invisible to the human eye. Ultraviolet data is particularly sensitive to gas emissions, allowing scientists to see how material was escaping from the nucleus and how that material interacted with solar radiation. The resulting images reveal a complex and dynamic environment, rather than a simple cloud of dust trailing behind a frozen rock. At the same time, data from other spacecraft added depth to the picture. Mars orbiters. Solar observatories like SOHO and heliophysics missions such as STEREO all detected subtle signatures associated with the object as it moved through different regions of the solar wind. Each instrument viewed 3I Atlas from a different angle and under different conditions. When these perspectives are combined, they create a three-dimensional snapshot of how the object behaved across space and time. This multi-platform approach significantly improves chemical analysis. By comparing ultraviolet emissions with optical and infrared data, scientists can better separate signals coming from gas, dust, and specific molecular species. It becomes possible to estimate how much material is being released, what kinds of molecules are present, and how those molecules change as the object responds to sunlight. Instead of a single measurement, researchers now have a layered dataset that reveals both composition and process. What makes these observations stand out is how different they are from what astronomers typically see when studying comets formed within our own solar system. Most observations rely heavily on ground-based telescopes and brief observation windows. In this case, space-based instruments tracked the object across multiple environments, capturing details that would otherwise be lost for an interstellar visitor that will never return. This level of coverage is extraordinary. With such advanced observations now in hand, scientists are left with a growing list of hypotheses. Some fit comfortably within known comet physics. Others stretch existing models and invite deeper scrutiny. And that leads to a question that cannot be ignored. With all of this high-quality data now available, what evidence do we actually have that links 3I Atlas to behavior beyond standard comet science? Within the scientific community, the dominant view remains clear. Most researchers working with data from NASA, ESA, and major observatories agree that 3I Atlas is a natural comet of interstellar origin. Its behavior can largely be explained through known physical processes, such as volatile outgassing, solar heating, and gravitational interaction. From this perspective, nothing observed so far requires exotic explanations. However, agreement on classification does not mean agreement on details. A smaller group of researchers has pointed to features in the data that do not fit perfectly within standard models. These include changes in jet activity that appear more structured than expected, brightness variations that seem unusually regular over short timescales, and subtle shifts in emission patterns that are difficult to reconcile with simple rotation alone. None of these observations prove anything extraordinary, but they raise questions about whether our models fully capture the complexity of such an object. Those claims have not gone unchallenged. Other teams have responded by arguing that these patterns can emerge naturally when limited data is sampled from a rapidly moving object observed under changing viewing angles. Instrument sensitivity, noise, and incomplete coverage can all create the illusion of structure where none truly exists. In this view, what appears anomalous may simply reflect the limits of observation rather than the presence of new physics. This tension highlights a crucial distinction that often gets lost outside academic circles. Scientific evidence accumulates slowly and cautiously. While speculation can move much faster, data may suggest possibilities. But interpretation requires restraint. When that restraint is removed, gaps in understanding can quickly be filled with narratives that go far beyond what the evidence supports. And yet, this is precisely why the story has captured so much public attention. Interstellar objects sit at the edge of our knowledge. They come from environments we cannot directly observe and carry histories we can only infer. When familiar explanations feel incomplete, curiosity naturally expands into speculation. The debate itself becomes part of the fascination, not because it promises immediate answers, but because it exposes how much we still do not know. If even trained scientists continue to debate the nature of what we observed, then the real question may not be whether 3I Atlas is extraordinary, but what these disagreements could lead us to uncover next. 3I Atlas passed Earth at a safe distance and then continued on its way, fading back into the vastness between stars. Nothing dramatic happened in the sky. No alarms were triggered. And yet, this brief encounter may mark the beginning of a new chapter in how we study the universe beyond our solar system. What this object offered us was not a spectacle, but knowledge. Its chemical signatures hinted at materials shaped far from our sun. Its orbit revealed a history written outside the gravitational order we know. Its activity showed how matter behaves when it crosses from one stellar environment into another. Together, these pieces expand our understanding of what interstellar objects are, and how common or uncommon they might be across the galaxy. The data collected during this passage is only the beginning. Observations from telescopes and spacecraft around the world are now being archived, calibrated, and prepared for long-term analysis. Over the coming months and years, scientists will revisit these measurements, refine models, and test new ideas against what 3I Atlas revealed during its fleeting visit. This is slow work, but it is how real understanding grows. When placed alongside Oumuamua and Borisov, 3I Atlas reinforces a powerful lesson. There is no single template for interstellar visitors. Each one arrives with its own structure, composition, and behavior. The diversity we are seeing suggests that planetary systems across the galaxy may be far more varied than our own experience once implied. Our solar system is not the standard. It is simply one example among many. And still, the most important questions remain open. Where exactly did 3I Atlas form? What conditions shaped its chemistry? How many similar objects are passing unnoticed through our solar neighborhood at this very moment? And what role do these travelers play in the broader life cycle, matter within the Milky Way? 3I Atlas has already left our reach. But it has not left us empty-handed. It has reminded us that the universe does not reveal itself all at once. It offers fragments, brief encounters, and partial answers, waiting for us to assemble them with patience and humility. 3I Atlas has only just begun to tell its story, and the most important question now is this: what will we learn from its journey in the years to come?